There are journeys that arrive like a quiet announcement, and others that feel like a celebration with confetti and countdown clocks. Artemis II is neither of those, really. It is not simply going back to the moon, and it is not a landing. It is a test flight with a very specific purpose, defined by careful thresholds, checklists, and time in the right places. It is a crewed lunar flyby designed to prove that a spacecraft can keep people alive and oriented and accurately guided, far beyond the comfortable reach of Earth's protective magnetic field. It is a mission defined as much by what you do not do, no landing, no long stay in lunar orbit, as by what you do. It is a loop of motion, a patient arc around a familiar world, and a return that depends on getting 1,000 small things right. And tonight, we'll follow the evidence gently, one calm detail at a time. Back in my office, it is quiet. A small desk lamp pulls warm light across a folder with a simple label: Artemis II. It's the kind of label that doesn't promise spectacle, only a careful test and a long loop that has to close cleanly. The window beside me holds a dark pane of sky and the faint suggestion of distance beyond it, the kind of distance you don't defeat, only measure, the kind you enter on purpose and return from by respecting the shape of the path. A mug sits near my notes, sending up a thin ribbon of steam that curls, thins, and disappears, like a quiet correction burn, small, deliberate, and just enough to keep the whole trajectory true. My name is Madeline Rowe, and this is the science of Artemis II for sleep. And if you'd like more calm case files like this one, you can subscribe and return whenever you need a little science and a little quiet. All right, now let's begin. I open the folder slowly, not with drama, but with definitions, because deep space is best understood when we give things their proper names. And the name Artemis II belongs in a particular drawer in the cabinet. It is a first crewed flight drawer, a systems demonstration drawer, a prove it with humans aboard drawer. Artemis II is the first time astronauts will ride the Space Launch System rocket and the Orion spacecraft together as a working pair, not in simulation and not with ballast standing in for breath. 4 people will be inside the crew module, and the mission is planned to last about 10 days, long enough to pass out of Earth's neighbourhood, wrap around the moon, and come home again. When a mission like this is planned, its goals are written in a careful voice. Not conquer, not race, not plant a flag, but demonstrate, test, verify, characterize, practice, learn. Tonight, we'll take those words seriously. We'll treat Artemis II like a case file with evidence cards as laid out on a desk. 1 card for the spacecraft, 1 for the route, 1 for the human body, which is always the most complicated system in any vehicle, 1 for radiation, which is invisible but measurable, 1 for the moon itself, which will pass by the windows like a familiar face seen at a different distance. And we'll keep the pace gentle, because this is not a countdown. It's a slow walk through a mission that is designed deliberately to be a rehearsal. The first evidence card is the simplest. What Artemis II is. It is a crewed lunar flyby. That phrase matters. It tells you that Orion will not settle into a long lunar orbit the way some missions do. It will pass by the moon, swing around it, and come back to Earth, tracing a trajectory chosen for reliability and for learning. If you've ever watched a pendulum, you already understand the basic comfort of this idea. A pendulum is not improvising. It is not deciding where to go each swing. It is following physics, following the geometry of gravity and energy, and returning because that is what the system does. In spaceflight, there is a family of trajectories that borrow that same sense of inevitability. One of them is called a free return. A free return trajectory is not magic. It is not guaranteed safety. It is simply a way of arranging the geometry so that, after a close pass by the moon, the spacecraft's path naturally bends back toward Earth. You still need working systems. You still need accurate navigation. You still need a heat shield that performs like it was promised. But in the long middle of the mission, outbound and around the moon, the overall curve of the road is designed to lead home. For a first crewed flight test, that is a comforting shape. There is another way to say free return, and it is more precise, if a little less poetic. A free return is a promise made by geometry. It says, if you leave Earth at the right speed and in the right direction, and if you arrive at the moon at the right time, then the moon's gravity will bend your path in a way that points you back home. Not home as in a landing spot you can see, but home as in an orbit that intersects Earth's atmosphere at a planned corridor. A small region of angles and speeds where your heat shield and parachutes can do their work. It helps to picture it like a smooth stone dropped into a stream. The water doesn't stop to negotiate with the stone. It simply goes around, guided by the shape that's already there. A free return trajectory is the stream, and the moon is the stone. The spacecraft arrives on a fast, open curve, what we call a hyperbolic approach, and the moon's gravity redirects that curve into a new one, sending the spacecraft back toward Earth. In the simplest version, you could almost imagine Orion as a bead sliding along a wire that's been bent into a loop, out from Earth, around the moon, and back again. But in real life, the wire is invisible, and it is made of measurements, because free return does not mean hands off. Even a beautifully planned path needs small corrections, because the universe is not perfectly smooth. A spacecraft isn't a math point. It has surface area, and sunlight pushes on it very gently. The spacecraft vents tiny amounts of gas. Thrusters fire in brief pulses. Sensors have uncertainty. And the initial launch, however accurate, is still the result of a real rocket in real air. So spaceflight includes something called trajectory correction maneuvers, small burns done along the way to tighten the path. These burns are often quiet in the public story, but they are central to the engineering story. They are the moment you take what you thought you did at launch, compare it to what you actually did, and then nudge the spacecraft back towards the center of the corridor. I like to think of them as the difference between planning a walk and actually walking. On a map, the sidewalk is a perfect line. In real life, you step around a crack, avoid a puddle, drift a little closer to the curb, and then gently correct, not dramatically, just enough to stay on course. On Artemis II, those course corrections matter not because anyone expects a failure, but because this is the first time the system is being tested with humans aboard. And with humans aboard changes the emotional value of small uncertainties. A correction burn is still a small thing, but it's also a rehearsal of decision-making, timing, propulsion performance, navigation solutions, and the crew's understanding of what the spacecraft is doing. It also becomes a rehearsal of patience, because deep space navigation is never instant. You measure, you estimate, you update, and you confirm. The spacecraft, in turn, is always doing its own quiet internal accounting. It knows its attitude. It knows to exquisite precision how it is oriented in space. It knows how fast it is rotating and where it is pointed, even when there is nothing outside to reference but stars. And then, with help from Earth-based tracking, it learns where it is in its path. Free return is the wide curve. Corrections are how you keep the curve in the right place. So when we say Artemis II will travel out and loop around the moon, it sounds like a single motion. But inside that motion is a rhythm of checks and updates. A calm, repetitive pattern that says, confirm the path, confirm the systems, confirm the people. And when you frame it like that, the free return shape becomes even more soothing. Not because it's effortless, but because it's deliberate. Not because it's guaranteed, but because it's designed to be forgiving. Now, with that gentle loop in mind, we can move to the next evidence card. The vehicle. Orion is the spacecraft that will carry and sustain the crew on Artemis missions and return them safely to Earth. That single sentence hides a great deal of engineering. When you picture Orion, it helps to picture it in two parts. There is the crew module, the capsule where the astronauts live, work, sleep, eat, and wait. It is the part that returns to Earth. It is the part with the heat shield. It is, in a sense, the lifeboat and the home. And then there is the service module attached behind it for the trip. It provides propulsion, power, and the steady supply of necessities that keep the crew module from becoming a sealed box with a deadline. For Artemis II, that service module is the European Service Module, built through European collaboration and integrated with Orion as a functional spine. It carries a large load of propellant, and it also carries consumables: water, oxygen, nitrogen. Numbers matter here because they are not poetry. They are inventory. On ESA's fact sheet, the European Service Module's launch mass is listed at about 13,500 kilograms, including about 8,600 kilograms of propellant, with consumables that include drinking water and the gases used to maintain the cabin atmosphere. In deep space, the romance is always supported by logistics. You can think of the service module as the part of the spacecraft that keeps time. It runs the budget of power, of heat, of propellant, of air and water. The crew module is where the story happens, but the service module is how the story stays possible. Now, the rocket. Artemis II launches on the Space Launch System, or SLS, a heavy lift rocket designed to send Orion, crew, and payload directly toward the moon in a single launch. We don't have to linger on every engine and tank to understand its role in the case file. The role is straightforward. It provides the departure energy. It carries the spacecraft out of the thick lower atmosphere, pushes it to orbital speed, and then helps aim the trajectory toward the moon. There is a particular elegance in the phrase single launch because it means fewer moving parts in the choreography. No assembly in orbit, no series of rendezvous just to create the starting configuration. A single stack, a single climb, a single release into space. But even in a single launch, the mission is not one continuous burn. It becomes a sequence of phases, each separated by moments of coasting and checking and choosing. And the first phase of Artemis II is essentially a careful wake up and verify. After launch, Orion enters Earth orbit. It is still close to home, close enough that the planet fills the windows in an almost overwhelming way. Close enough that the ground controllers can hear every telemetry whisper, and that the crew can feel, psychologically, the tug of the familiar. This is where the spacecraft is asked a simple question. Are you the vehicle we built, or are you the vehicle we hoped we built? The spacecraft answers with data. power systems report their voltages and currents, like a steady heartbeat on a monitor. Thermal systems report temperatures across the structure, and the control loops respond, opening and closing pathways for heat, like lungs regulating breath. Guidance systems report orientation. Propulsion systems report pressures and valve states and the quiet readiness of thrusters that have not yet been needed. And inside the crew module, life support starts doing what life support does. It manages a sealed environment so it remains comfortable and safe. That means controlling carbon dioxide levels, keeping humidity within reason, maintaining oxygen partial pressure, and dealing with the small, persistent realities of being human inside a machine. Life support is not glamorous, but it is the difference between a spacecraft and a coffin. When people picture a spacecraft, they often picture engines and flames. But the lived reality is quieter. It is airflow. It is temperature. It is humidity. It is the simple fact that 4 human bodies are warm, wet, breathing chemistry sets, and a spacecraft has to manage that calmly, day after day. So let's slow down for a moment and treat Orion the way we'd treat an evidence room, not as a heroic object, but as a set of controlled loops. Start with air. The crew breathes oxygen and exhales carbon dioxide. That's the simplest description. But the operational description is a little more careful. The cabin atmosphere must keep oxygen at safe levels, keep carbon dioxide low enough to avoid headaches and cognitive impairment, and keep pressure and composition stable as the crew sleeps, exercises, and works. So Orion needs circulation fans that keep air from becoming stagnant. It needs sensors that continuously sample cabin gases, because in a sealed environment, you don't guess, you measure. It needs a way to remove carbon dioxide. In spaceflight, CO2 removal is sometimes described as scrubbing, and it really is a form of cleaning. You pass air through material that traps CO2, then either store it, vent it, or regenerate the material, depending on the system design. Then there's water, not just drinking water, but water as a hidden byproduct of living. Humans exhale moisture. They sweat. They create humidity. In a sealed cabin, humidity can't just drift away into weather. It has to be managed, or you'll get condensation where you don't want it, on walls, on equipment, in places that turn electronics into problems. So the life support system acts like a quiet dehumidifier, pulling moisture out of the air. That moisture isn't just waste, it's a resource. In many spacecraft systems, condensed water can be collected and managed, part of a broader loop of consumables. And then there's heat. A cabin full of people, computers, batteries, and pumps produces heat. Space is cold, but it is also a vacuum. There's no air outside to carry heat away by convection, the way your room does. So the spacecraft has to move heat internally, through fluids, through radiators, through controlled surfaces, and keep the cabin in the narrow comfort band where humans can sleep and think. There's also the reality of eating. Food in microgravity behaves differently. Crumbs don't fall, they float. Liquids bead and cling. Smells behave differently too, because air doesn't move the same way around your nose. So the cabin becomes a place where small habits matter. Sealing packages, capturing crumbs, cleaning surfaces, keeping the environment from becoming a slow, invisible mess. And then there is waste management, a subject that is never glamorous, but always necessary. On a 10-day mission, you need practical systems for human waste that keep the cabin hygienic and keep odours under control, because morale and health are part of mission success. In low Earth orbit, resupply can correct problems. In lunar distance, you don't have that luxury, so the systems need to be reliable and the crew needs procedures that are simple, repeatable, and forgiving. Now add sleep. Sleep in a spacecraft is not only rest, it is a deliberate operational mode. A sleeping crew is still producing carbon dioxide and humidity. They are still warm, their bodies still have rhythms, and the cabin still needs to keep them comfortable without waking them. So a spacecraft isn't just designed for awake operations. It's designed for the quiet half of the day, when work pauses and the goal is stability. This is one reason Artemis II is such a meaningful test. It's long enough for the cabin to become truly lived in, long enough for small annoyances to reveal themselves. A fan that's slightly too loud, a corner that's hard to brace in, a routine that seems fine on day 1 but becomes tedious by day 6. Long enough for the crew to learn what is effortless and what requires attention. And if you think about it, that kind of learning is exactly what a rehearsal mission is for. Because on future missions, you want the cabin to feel less like a prototype and more like a home that happens to travel through deep space. So we pause here, in the quiet middle of the case file, and we remember what Orion is doing. It is not just flying, it is maintaining a pocket of Earth-like conditions inside a place that is profoundly un-Earth-like. It is taking the most fragile cargo, human physiology, and holding it steady. And now, with that in mind, we can return to the larger point. On a mission like Artemis II, life support is not just a background utility. It is part of the test. It must work not in a laboratory, and not on a short hop, but across a 10-day arc with sleep cycles and exercise and meals and quiet hours. And because humans are part of the system, Artemis II also carries science that treats the crew as both operators and research participants. This is one of the most striking and honest things about modern human spaceflight. The mission is not only about the spacecraft visiting a place, it is also about the human body being exposed to a new environment and measured carefully so that future missions can be safer, more predictable, more humane. So while the vehicle is being checked, the crew is being checked too. Gently, systematically, respectfully. One of the studies planned for Artemis II is called Archer, Artemis Research for Crew Health and Readiness. It involves monitoring sleep patterns, stress levels, cognitive performance, and teamwork dynamics using wearable devices like wristbands that can gather real-time physiological and behavioural data. If you've ever worn a simple fitness tracker, you already know the surface version of this: heart rate, movement, sleep-wake patterns. But on Artemis II, the point is not personal optimization. The point is evidence. Deep space is different from low Earth orbit. The distance from Earth changes how you communicate. The time delay changes how you problem solve. The sense of isolation changes how your mind treats risk. Archer is designed to capture the texture of that environment, so that the human side of the mission is not left to anecdotes and memories alone. Another study focuses on immune biomarkers. Spaceflight can alter immune function, potentially changing how susceptible a person is to illness, or how dormant viruses behave under stress. For this study, the crew will provide blood samples before and after the mission, and saliva samples during the mission. The method is wonderfully practical. Specialised paper in pocket-sized booklets designed to preserve the sample even without refrigeration. It's an image that fits perfectly in a case file, a tiny booklet of paper carried in a pocket, holding evidence of how a human body responds to radiation, isolation, and distance. There is also a study called Avatar, a virtual astronaut tissue analog response. It uses organ-on-a-chip devices, small platforms that can mimic aspects of human tissue function. For Artemis II, the concept involves incorporating cells derived from pre-flight blood donations into these chips, then studying how deep space stresses like microgravity and radiation affect them. bone marrow is highlighted as especially sensitive to radiation and central to immune function, which is why it becomes a focus. This kind of study is both futuristic and deeply grounded. It is an attempt to understand biology in a controlled way without invasive procedures. It points toward a future where medical countermeasures might be more personalised, shaped to the individual astronaut rather than the average astronaut. There is also something called standard measures, a long-running effort to collect consistent health data across missions. It involves samples, blood, urine, saliva, and surveys and tests that track balance, vestibular function, muscle performance, microbiome changes, and ocular and brain health. It includes assessment of motion sickness symptoms during the mission and additional tests after landing, continuing for weeks. In other words, Artemis II is not only a spacecraft test, it is also a carefully instrumented human experience. And all of this is happening while the spacecraft is still close enough to Earth that the crew can watch weather systems drift across the planet like slow ink in water. When the initial checkouts are complete, the mission moves into something both technical and quietly poetic: manual flight. NASA has been explicit that Artemis II will provide astronauts the opportunity to take the controls of Orion and periodically fly it manually during the journey around the Moon and back. This is not because the spacecraft cannot fly itself. It is because you want to test the interface between human judgment and machine response. In a future emergency, or in an unexpected scenario, the crew may need to steer. They may need to reorient the spacecraft, manage attitudes, or execute a burn. The time to learn how that feels is not during the emergency. The time is during a planned test flight with clear margins and a patient mission control team. So part of Artemis II is essentially learning the feel of the vehicle. How quickly does it rotate when a control input is made? How does the spacecraft hold attitude when you let go? How do the displays and cues guide the crew's decisions? How does the cabin environment, floating bodies, drifting tools, gentle inertia, change the way piloting feels compared to an aircraft? These are not abstract questions. They are the quiet foundation of confidence. There is also a specific planned demonstration that involves proximity operations, flying Orion near the upper stage after separation. This is another detail that belongs in the rehearsal drawer. Relative navigation is a skill. Holding position near another object, managing closing rates, understanding the geometry of motion when there is no air resistance, these are things you want to practice in real space, with real sensors, before you ever need them in a high-stakes context. So the mission doesn't rush away from Earth. It lingers just long enough to practice being a spacecraft with humans aboard. Then comes the push outward. This part of the file is often described in one clean phrase: the translunar injection. It is the moment when the spacecraft leaves Earth orbit and commits to the path toward the Moon. It is the point where Earth stops being the primary centre of motion and becomes, slowly, the world behind you. In reality, it is a sequence: align, confirm attitude, check systems, execute the burn, verify the result. A burn is never just fire. It is a mathematical act. It is velocity added in a particular direction at a particular time to shape an orbit into a new one. Once Orion is on its way, the rhythm changes. Deep spaceflight is in many ways a practice of patience. There are activities, yes, science tasks, systems monitoring, exercise, scheduled sleep. But there are also long stretches where the most important work is simply keeping everything stable. It is easy to imagine deep space as dramatic, but it is more accurate to imagine it as controlled. The spacecraft maintains orientation, often using star trackers and inertial measurements to know where it is pointed. It uses thrusters to adjust attitude. It watches the thermal balance, ensuring the sun doesn't overheat one side while the other side radiates into cold darkness. It manages power, solar arrays gathering energy, batteries smoothing the flow. Inside, the crew lives in a small space, carefully organised. In microgravity, there is no up to keep things in place. Every object has a home, and every home has a restraint, because drift is the natural state. In this phase, the mission becomes a moving laboratory. Archer continues quietly, collecting patterns of sleep and stress and cognitive performance. In a sense, it is listening to the crew's nervous systems, translating physiology into data that can be studied later. Immune biomarkers tasks happen with a calm practicality. A saliva sample, collected and preserved in paper, becomes another entry in the log. Standard Measures continues, building a consistent dataset that can be compared to the long history of human spaceflight research, now extended beyond low Earth orbit. An avatar, those organ-on-a-chip devices, represent something like a parallel crew, tiny human tissue analogues experiencing the same mission, recorded in microchannels and cellular responses. When you look at Artemis II this way, it becomes a case file with two intertwined narratives. The spacecraft is travelling around the moon. The human body is travelling into a new data regime. Now we come to one of the most important and least visible parts of the story: radiation. Earth is wrapped in a magnetic field that acts like a shield. It does not block all radiation, but it shapes the environment in a way that makes low Earth orbit comparatively forgiving. Outside that field, the radiation environment changes. Galactic cosmic rays are present. Solar particle events can spike. Space weather becomes a daily concern. Artemis II will fly well beyond Earth's protective magnetosphere, and because of that, radiation monitoring is treated as a core mission element. On the Canadian Space Agency's overview, radiation monitoring on Artemis II involves 6 active radiation sensors deployed at various locations inside the Orion crew module. The crew will also wear dosimeters in their pockets. This is not just passive recording. These sensors can provide warnings of hazardous radiation levels, and the data can be used by mission control to decide whether the crew should shelter to protect from radiation exposure due to solar storms. Sheltering in a spacecraft is its own kind of procedure. It is not a bunker you climb into, thick-walled and underground. It is a strategy of arrangement. You take the mass you already have, supplies, water, equipment, and you place it between your bodies and the direction of incoming particles as best as you can. You choose a location in the spacecraft where shielding is relatively higher. You adjust operations, you wait. And because space weather can't be sensed by human skin the way wind can, it must be forecast. NASA's Artemis II. Science Overview notes that NASA and NOAA will provide 24/7 real-time space weather forecasting and analysis during the mission. The team tracks coronal mass ejections and solar flares, phenomena that can harm human tissue and disrupt electronic systems, providing advanced warnings so the crew can take protective measures if needed. This is one of those quiet modern realities that feels almost like science fiction until you say it plainly. There are people on Earth whose job is to watch the sun on behalf of 4 astronauts travelling around the moon. So in our case file, radiation becomes a character, invisible, measurable, forecastable, manageable, but never completely tame. Now, as Orion travels outward, the moon grows. Not quickly, like a plane approaching a runway, but slowly, like a thought becoming more defined. At first, it is a small disk. Then it becomes a bright coin. Then, somewhere in the later days of the outbound leg, it becomes something with texture. And in the planning for Artemis II, the moon is not only a destination, it is also an object of observation. The Canadian Space Agency describes it with a vivid comparison. At the distance of the flyby, the moon will look like a basketball held at arm's length. Orion is planned to fly thousands of kilometers from the lunar surface, close enough for detail, far enough to keep the trajectory simple and safe. Depending on the exact flight path determined at launch, the crew could also be among the first humans to see, with the naked eye, parts of the moon's far side, the hemisphere that always faces away from Earth. There is something quietly profound in that. The far side is not mysterious anymore, not in the scientific sense. We have mapped it, we have imaged it in detail, but there is a difference between knowing a landscape through data and seeing it with human eyes. Artemis II is designed, in part, to give the crew that experience, and to turn it into usable science. NASA's science page notes that during a roughly 3-hour period as Orion flies by the far side, astronauts will analyse and photograph geologic features such as impact craters and ancient lava flows. They will rely on extensive geology training, classroom work, and field trips to moon-like terrain on Earth to describe nuances in shapes, textures, and colours. This is not sightseeing. It is human observation as an instrument. A camera captures photons. A human observer can also capture context. The way a shadow edge reveals slope. The way a colour shift suggests composition. The way patterns fit into a geologic story. And the crew will not do this alone. NASA describes a team of scientists with expertise in impact cratering, volcanism, tectonism, and lunar ice, providing real-time data analysis and guidance from the Science Evaluation Room in Mission Control. They have practiced together in simulations. They have rehearsed how to talk to astronauts about what to look at, how to frame it, how to describe it so it becomes valuable data. In our case file, this is another example of rehearsal becoming reality. Years of training now used in a 3-hour window of observation. It is also a reminder that Artemis II is as much about building operational habits as it is about travelling distance. Now, while the crew is observing the moon, there is a second layer of science happening, smaller, quieter, tucked into the architecture of the rocket. International partners are flying CubeSats aboard Artemis II. These small satellites are not part of NASA's primary mission objectives, but they ride along and then go their own way. According to both the Canadian Space Agency and NASA's Artemis II Science Overview, space agencies from Germany, South Korea, Saudi Arabia, and Argentina will fly CubeSats aboard the mission, deployed in high Earth orbit after the upper stage detaches from Orion. The CubeSats are shoebox-sized, and they ride inside a ring that connects Orion to the upper stage. That detail matters because it tells you something about how space missions are layered. The main vehicle at the centre, and around it, in the margins, small experiments that make use of the ride. Each CubeSat has a distinct objective. Tatchels from the German Aerospace Centre will measure effects of the space environment on electrical components, informing technologies for lunar vehicles. KRADCube from Korea's space agency will use a dosimeter made of human-like tissue to measure space radiation and biological effects across the Van Allen radiation belts. A CubeSat from the Saudi Space Agency will measure space weather at a range of distances from Earth, deployed in high Earth orbit. And Atenea from Argentina's Space Activities Commission will assess radiation shielding methods, measure Earth's radiation spectrum, collect GPS data, and validate a long-range communication link. There is also mention of additional radiation research by German teams. So even as the crew travels outward, there are these small satellite witnesses, each one taking measurements, each one adding a thread of data to the tapestry of understanding. It is useful, sometimes, to pause here and remember what high Earth orbit means in this context. Earth is surrounded by the Van Allen radiation belts, regions where charged particles are trapped by Earth's magnetic field. Low Earth orbit, where the International Space Station lives, skims beneath the worst of these belts. But missions that go higher or pass through certain regions encounter different radiation conditions. The CubeSats and the Orion crew module, during portions of the mission, will pass through or near environments where radiation measurements become especially informative. That is part of why Artemis II is such a valuable step. It is not only farther, it is different. Different environment, different communications geometry, different operational constraints. Now, let's slow down and walk through the mission timeline in a way that feels like turning pages. Page 1 is launch and early orbit. We can imagine the sequence without needing every second. The rocket rises, accelerates, and leaves the thick lower atmosphere behind. In the cabin, the crew experiences vibration and force, then the smoothness that arrives when the air thins and the climb becomes mostly about inertia and thrust. Eventually, the boosters separate. Stages do their job and fall away. Orion, still attached to its service module, is delivered to orbit. Then comes the quiet moment, the point where the spacecraft is on its own, meaning it is now a self-contained system with humans aboard, flying in space. Page 2 is early checkouts and planned demonstrations. This is where systems prove themselves. It is where the crew begins the routine of living in the cabin, and where mission control begins the routine of watching telemetry in a steady, practiced way. It is also where manual piloting demonstrations begin. The crew takes the controls, not to show off, but to learn. You can think of it like taking a new car into an empty parking lot before driving it on a highway at night. You test the steering feel. You test the brake response. You learn how the vehicle talks to you through vibration and delay. Orion talks through displays, through control inputs, through how it responds to attitude commands. The crew learns its language. Page 3 is the departure burn that commits Orion toward the moon. And then the mission becomes a long glide with occasional corrections. Spacecraft navigation is a subtle art. You cannot look out the window and see a road. You infer your position and velocity by combining inertial measurements, star tracker data, ground-based tracking, and planned burns. The Deep Space Network becomes part of the story here. It's worth slowing down to appreciate what the Deep Space Network really means, because it's not a single antenna. It is a choreography across Earth. A set of large radio dishes positioned so that, as our planet rotates, there is almost always at least one place on Earth that can see the spacecraft. The idea is beautifully simple. If you want to keep talking to something far away, you don't put all your listening in one place. You spread it around the world, so the Deep Space Network feels like a kind of global lighthouse system, except instead of beams of light, it uses radio waves. And instead of ships, it tracks tiny spacecraft signals arriving with extraordinary faintness. In practical terms, it is how Orion sends down data. It is how Orion receives commands. It is how voice travels and how telemetry becomes a living stream. And it's also how navigation becomes possible. Because in deep space, where are we is not answered by a map app. It's answered by physics. You can track a spacecraft by measuring the radio signal it sends. You can measure how long the signal takes to arrive. You can measure how its frequency shifts because of relative motion, like a siren sounding higher as it approaches and lower as it moves away, but for radio waves. With those measurements, and with models of gravity, you estimate the spacecraft's trajectory, and then you update the estimate, and then you update it again. This is why mission navigation feels like careful bookkeeping. You never have perfect knowledge, you have increasingly refined knowledge. Inside the spacecraft, Orion also has its own sense of orientation. It uses instruments that measure rotation and acceleration. It uses star trackers, cameras that look at the star field and compare what they see to known patterns, allowing the spacecraft to know how it is pointed with remarkable precision. Pointing matters because pointing is how you aim antennas, how you orient for thermal control, how you prepare for burns. Pointing is how you keep a spacecraft calm. Now, when you combine Orion's internal orientation knowledge with Earth-based tracking, you get something like a shared understanding. Earth says, "We think you are here, moving like this." Orion says, "I am oriented like this, and my thrusters performed like that." Together, they converge on a solution, a best estimate of where the spacecraft is in its path, and where it will be if nothing changes. Then, when something needs to change, you schedule it. This is where those small trajectory correction maneuvers feel so important. Because a burn is not only propulsion. A burn is a test of the loop that connects the spacecraft to the people guiding it. Did we model it correctly? Did the engine perform as expected? Did the spacecraft hold attitude properly during the burn? Did the post-burn tracking confirm the result? These questions are not asked in panic. They are asked as procedure. And the procedure, repeated calmly, is what turns a risky environment into a manageable one. There is also a human side to deep space communications. In low Earth orbit, you can almost pretend the spacecraft is nearby. Communications are frequent. Time delays are small enough to ignore. But as Orion travels towards the moon, the delays become noticeable, not dramatic, but real. A pause after you speak, a slight lag before a reply. Enough that you begin to feel in your bones that you are not in the same room as mission control. You are not even in the same neighborhood. You are in a different regime where you must think a little farther ahead, and that shift is part of the Artemis II test too. It tests whether procedures are written well enough that the crew can execute them without constant back and forth. It tests whether the crew and mission control share the same mental model of what normal looks like. It tests whether the spacecraft can remain stable through quiet stretches, when nobody is actively touching it. It tests the rhythm of autonomy, when to decide on board, when to consult the ground, when to wait for more data. And all of that is hard science in the truest sense. Not theory, not slogans. Operations. Measured, practiced, repeatable operations. So when we say the Deep Space Network becomes part of the story, we really mean that Orion is now connected to Earth through a system designed for patience. A system designed for faint signals, long distances, and careful confirmation. Antennas on Earth, spaced around the globe, listen and transmit, turning radio waves into a bridge across distance. There is a psychological comfort in knowing that even when you are far away, you are not unheard. But there is also the simple fact of light speed. Signals take time. Not much in human terms, seconds, but enough that you cannot treat mission control like a co-pilot sitting beside you. In deep space, the crew must be more autonomous, and the spacecraft must be more stable, and the procedures must be more complete. Artemis II is, in a way, a test of that autonomy. Page 4 is the outbound cruise. This is where the daily rhythm matters. Sleep becomes important, not just as rest, but as a measurable variable in Archer. Sleep in microgravity is different. You are not lying down. You are restrained in a sleeping bag. Your inner ear behaves differently. Your sense of night is defined by schedules and lighting rather than by sunset. Stress is monitored too, not because stress is a failure, but because it is a parameter. It rises and falls in response to workload, novelty, uncertainty, and even the quiet strangeness of being far from Earth. Cognitive performance tasks, simple tests, become another part of the log. They help quantify how the deep space environment affects attention and decision-making. Teamwork dynamics are observed because humans are social animals even in a capsule. How people coordinate, support, and communicate is not just personality, it is mission safety. Meanwhile, standard measures and immune biomarkers tasks continue, building a broader picture. Immune function, microbiome changes, vestibular adaptation, motion sickness, cardiovascular responses. The human body is adapting, and the mission is recording the adaptation. Page 5 is the approach to the moon. Here, orbital mechanics becomes almost soothing. The moon's gravity begins to tug. The spacecraft's trajectory bends. The geometry that was calculated on Earth becomes visible as the path curves around a world that has pulled at Earth's tides for billions of years. If you could draw the trajectory on paper, it would look like a thread looped around a smooth stone. On Artemis II, that looping is planned so that the spacecraft swings around the moon and returns toward Earth. During the close pass, the moon fills the windows more fully. Craters become distinct. Bright ray systems stretch like pale scratches across darker plains. Ancient lava flows, frozen basalt seas, show their boundaries. And then, for a time, Orion passes behind the moon. This is another detail that matters. The far side is radio quiet with respect to Earth. When the spacecraft is behind the moon, direct line-of-sight communications are blocked. There is a period where the crew is, in a literal sense, out of contact. NASA's Science Overview highlights a 3-hour period associated with the far side flyby for observation. That kind of window is carefully planned. It is science time, and it is also a communications geometry reality. In those moments, the crew's autonomy is not theoretical, it is lived. And this is part of what Artemis II is testing. How it feels, operationally and psychologically, to be alone with your spacecraft for a period, knowing that Earth cannot reach you until you come around again. For some people, that thought feels dramatic. For a mission planner, it is simply a parameter, a known gap, a managed interval. During the flyby, the crew will observe and photograph features with guidance from scientists on Earth, based on real-time analysis. They may look for impact craters with particular morphologies, sharp rims, central peaks, terraced walls, clues to impact energy and crustal properties. They may photograph lava flows, noting boundaries and textures, looking for evidence of different eruption episodes. They may be guided toward regions of special interest, like the Orientale Basin, an enormous impact structure whose rings and ejecta patterns tell a story about the moon's history. They will use their geology training to describe textures, shapes, and colours. Those words, textures, shapes, colours, sound simple, but in planetary science, they are the beginning of interpretation. A smoother texture might suggest a different flow regime. A subtle colour shift might hint at composition differences. The geometry of a feature might suggest tectonic stresses, or volcanic construction, or impact mechanics. And because the moon is also a place of subtle phenomena, there is the possibility, mentioned in the Canadian overview, that the crew could witness meteoroid impacts as brief flashes or rare effects like dust levitation. Whether those happen or not is a matter of chance, but the fact that Artemis II even considers them as possible observations tells you something about the mission's attention to the moon as a dynamic environment, not just a static rock. Then the spacecraft swings around and begins the return. This is where the free return trajectory earns its name. The path bends outward from the moon and aims back toward Earth. The moon slowly shrinks behind them, and Earth becomes the bright destination ahead. On the return leg, the mission returns to the rhythm of monitoring, maintenance, and measured human science. Radiation monitoring continues. Dosimeters remain in pockets, quiet witnesses. The 6 active sensors continue to report, building a detailed map of exposure inside the cabin. Space weather forecasting continues too. The sun does not stop being relevant because the moon is behind you. In fact, on the return, the crew is still outside Earth's magnetosphere for much of the time, still in the environment where solar activity matters. There is something almost tender in the way spaceflight blends the cosmic and the practical. A solar flare begins as magnetic complexity in the sun's atmosphere. It becomes a burst of energetic particles that can cross the space between worlds. And in the end, it becomes a line on a console, a warning and a decision about whether 4 people should rearrange their supplies and wait. Now, we should take a slow detour here, still inside the mission, into a concept that often gets glossed over: what it means to characterize the deep space environment. This phrase appears in mission descriptions because it is an honest description of a major goal. Deep space is not empty. It is filled with particles, radiation, temperature extremes, and a communications geometry that changes over time. Characterizing means measuring. It means comparing predictions to reality. It means collecting the kind of data that lets engineers design with confidence rather than hope. On Artemis II, characterization happens through radiation sensors, through crew-worn dosimeters, through CubeSats that measure effects on electronics, through biological studies that show how bodies respond. It also happens through the simple performance of systems, how well power generation works, how stable thermal control is, how reliable communications links are across distance, how navigation solutions behave when you are not constantly tracked by low-orbit infrastructure. All of this is evidence, and evidence in this office is what we follow. Now let's return, gently, to the crew module. Inside Orion, the crew has a finite space, and that space becomes a world. They have schedules, they have checklists, they have meal times and sleep times. They have exercise, because muscle and bone maintenance is part of the biology of spaceflight. They also have small rituals, ways of making a capsule feel like a place where a mind can rest. And as the mission progresses, the cabin changes, not in its physical structure, but in the way it is lived in. Objects migrate slightly. Straps get used. A particular corner becomes a favourite place to brace. A particular panel becomes familiar. This is worth saying because human factors are not a side story. They are central. A spacecraft can be technically capable and still fail if it is not livable, if the crew cannot rest, if the workload is mismanaged, if the interface is confusing, if the environment makes small tasks too difficult. Artemis II is designed to reveal these issues in a controlled way. Now, somewhere in the later return days, another kind of preparation begins. It is the preparation to come home. Coming home from lunar distance is not like coming down from low Earth orbit. The entry speed is higher, the energy is higher, the heating is more intense. Orion's heat shield is designed for this environment. It is one of the defining pieces of the spacecraft, a protective layer that turns kinetic energy into heat, and then into plasma, and then into a safe deceleration, while keeping the cabin inside from becoming an oven. Re-entry is sometimes described in dramatic terms, but it can also be described as a controlled dive into denser air. The capsule approaches Earth on a carefully chosen trajectory. Guidance and control systems orient it to the correct attitude, presenting the heat shield forward like a shield against a storm. As it hits the upper atmosphere, air molecules begin to collide with the capsule at high speed, heating the gas and forming a sheath of ionized plasma. There may be periods where radio communication is degraded or lost, a known effect of plasma around a vehicle. Inside, the crew experiences increasing G-forces. The body, which has been floating, is suddenly pressed into the seat. The vestibular system, already adapted to microgravity, now has to interpret gravity again and do it while being accelerated. This is one reason standard measures includes post-landing tests of head, eye, and body movements, balance, and functional performance tasks. Coming home is a biological event, not just a navigational one. After the heating phase, the atmosphere becomes thick enough for parachutes to do their slow, deliberate work. Parachute deployment is a choreography of stages. Smaller parachutes to stabilize and slow, then larger canopies to reduce speed further. It is the opposite of a rocket launch. Instead of controlled explosion upward, it is controlled unfolding downward. Eventually, the capsule splashes down in the ocean. Splashdown is the end of the headline story, but it is not the end of the mission story, because the most intense part of coming home happens just before the ocean. It happens in air, and it happens in heat. A return from lunar distance carries more energy than a return from low Earth orbit. Orion is arriving faster, and the atmosphere is about to do the job of slowing it down. The way you make that safe is not by resisting the atmosphere, but by using it carefully. Orion's heat shield is built to take the blunt truth of physics. Speed becomes heat, and heat must be managed. As the capsule enters the upper atmosphere, it compresses air in front of it. That compressed air heats dramatically, and the gas around the capsule becomes ionized, plasma, a glowing sheath that can interfere with radio communication. This is one reason re-entry has a reputation for silence. Not because there's nothing to say, but because physics can briefly overwhelm the ability to speak through it. Guidance, navigation, and control systems are doing constant work during entry. They are keeping the capsule at the right attitude, heat shield forward, angle controlled, so that heating is distributed as designed and deceleration stays within tolerable limits. And Orion is designed to do something subtle that can sound surprising the first time you hear it. It can skip. A skip re-entry is exactly what it sounds like. The capsule dips into the upper atmosphere, slows and heats, then lifts back out briefly before dipping in again for a final descent. It's not a mistake, it's a technique. It lets the spacecraft manage peak heating and G-forces by stretching the deceleration over a longer path, like skipping a stone across water rather than plunging it straight in. It also offers flexibility in where you land, because you can adjust the trajectory within limits as you ride the thin upper layers. For Artemis missions, this kind of guided entry is part of what makes a high-energy return feel controlled rather than brutal. Then, as the capsule descends into thicker air, the work shifts from heat shield to parachutes. Parachutes are another form of gentle engineering. They are fabric doing physics. They open in stages, first to stabilize and slow, then to increase drag dramatically, turning a fast fall into something the ocean can accept. By the time the main parachutes are fully deployed, the capsule is descending at a speed designed for survivable impact with water, and then comes splashdown, a sudden physical end to days of floating, a brief jolt, and then bobbing, and then, almost immediately, the recovery story begins. Recovery operations are their own choreography, planned as carefully as launch. A recovery ship positions nearby. Small boats approach the capsule. Divers may enter the water to attach lines and stabilize the vehicle. Teams work methodically because the capsule is not only carrying people, it is carrying data, samples, and a spacecraft that will be inspected like a witness after an event. Once the capsule is secured, the crew egress begins. This is a moment people often picture as triumphant, but the reality is more clinical and, in a way, more interesting. The crew has been in microgravity for days. Their balance systems have adapted. Their sense of up has been quieted and rewritten. So when they return to gravity, the world can feel heavy and unstable. Standing can feel strange. Walking can feel like learning again. That's why post-flight checks are so important. Medical teams assess the crew. Standard measures continues. Balance tests, functional tasks, surveys, physical performance checks, building a record of how the body readapts. If saliva samples were collected during the mission, they become part of a time series that can be compared to pre-flight and post-flight blood work. If wearable devices tracked sleep and stress patterns, that dataset is downloaded and examined, looking for signatures of deep space living. If radiation dosimeters were worn in pockets, their readings become a map of exposure across time and cabin location, and the spacecraft itself is inspected. Heat shield performance is assessed, parachute systems are examined, avionics logs are pulled, thermal data is reviewed. Because a spacecraft returning from the moon is not just returning humans, it is returning evidence. This is one of the most beautiful things about engineering when it is done well. Nothing is wasted. Even the parts that char and ablate and darken are part of the record. Even the uncomfortable moments are turned into procedures. Even the fatigue becomes data that can protect future crews. So splashdown is not an ending, it's a handoff from flight to analysis, from operations to review, from a live mission to a case file that will be studied, annotated, and used to make the next mission quieter, safer, and more certain. And then, the mission is not finished yet. Recovery operations begin. Teams approach the capsule. They secure it. They assist the crew. The astronauts are helped out, and the world they return to feels heavy and loud, and full of smells and textures that were absent in the sealed cabin. Standard measures continues for weeks after return, because the body's recovery is part of the data story. Immune studies can compare pre-flight and post-flight samples. Avatar results can be analysed. Archer datasets can be examined for patterns in sleep, stress, and cognition. Radiation exposure data can be mapped against trajectory and space weather conditions. And all of this becomes the evidence that informs future missions. Now, to make this case file feel complete, I want to do what we do in the office when a story has many layers. We re-walk the path slowly, and we name what matters. Artemis II is a crewed lunar flyby. It is designed to test Orion and SLS with humans aboard, and to demonstrate a broad range of capabilities needed for deep space missions. It includes manual flight, astronauts taking the controls of Orion during the journey, learning how the spacecraft behaves under human command. It includes proximity operations, practicing the kind of relative motion understanding that makes future complex operations safer. It includes deep space human research, Archer for sleep, stress, cognition, and teamwork dynamics. Immune biomarkers, tracking biological changes with blood and saliva samples. Avatar, using organ-on-a-chip technology to study tissue responses. Standard measures, building a consistent dataset of physiological and functional performance changes, and radiation monitoring with active sensors and personal dosimeters. It includes lunar observations during a planned flyby period, analysing and photographing geologic features, guided in real time by scientists on Earth, informed by geology training in moon-like terrain. It includes international CubeSats deployed in high Earth orbit, each with distinct objectives, measuring effects on electronics, radiation across the Van Allen belts, space weather at varying distances, shielding validation, radiation spectra, GPS data collection, and long-range communications experiments. And it includes 24/7 space weather forecasting support, tracking solar activity, and providing warnings so protective measures can be taken if needed. This is the shape of the mission. It is, in its own way, a careful promise. Not that everything will be easy, but that everything will be measured. And because this is a sleep story, we can let the mission become a kind of calm machine in the mind. We can imagine the spacecraft gliding, steady and quiet. We can imagine the crew moving slowly through routines, checking displays, photographing the moon, collecting small samples in paper booklets, answering cognitive prompts, strapping in to sleep. We can imagine the Earth far away and still present in the steady voice of mission control, in the radio link, in the forecasts made by people watching the sun. We can imagine the moon passing close enough that it looks like a ball held out in front of you, bright and detailed, its far side briefly revealed as Orion arcs behind it. And then we can imagine the long return, the gradual swelling of Earth in the window, the careful preparation for re-entry, the heat shield doing its silent work, and the parachutes opening like slow flowers. When you look at it this way, Artemis II becomes something like a controlled storm. Not wind and snow, but energy and motion. Not visibility thresholds, but trajectory constraints. Not a whiteout, but a communications blackout behind the moon. And in both cases, the answer is the same. Define it carefully, measure it honestly, and move through it one calm procedure at a time. Back in my office, the folder lies open. The lamplight pools on diagrams and notes, and a few underlined phrases. Crude lunar flyby, 10 days manual flight, radiation sensors, a 3-hour window to study the far side, a basketball at arm's length. Sometimes, when the world feels too large or too fast, it helps to remember that human progress often happens in this quiet way. Not with a leap, but with a test. Not with a speech, but with a checklist. Not with certainty, but with data. Artemis II is a mission that respects the complexity of going far from Earth with humans aboard. It does not pretend that deep space will be forgiving. It prepares for the harshness, measures it, and learns from it. And that is, in its own way, a gentle thing. Because gentleness in engineering looks like redundancy. Gentleness looks like rehearsal. Gentleness looks like sensors inside a cabin, quietly watching invisible radiation so that human bodies can be protected. Gentleness looks like a team of scientists on Earth guiding astronauts on what to photograph, so a 3-hour window becomes meaningful. Gentleness looks like a small booklet of paper in a pocket, preserving a saliva sample so immune changes can be understood. Gentleness looks like a tiny organ-on-a-chip device, carrying tissue analogues into deep space so future crews can be healthier. Gentleness looks like a return trajectory designed to bend home. So tonight, if you're listening from a bed or a couch or a quiet room with the lights turned down, you can let Artemis II become a slow-moving thought, a capsule travelling along a path chosen with care. A mission built not to prove bravery, but to prove capability. A case file full of measured details. And as we reach the end of the folder, we do what we always do. We close it, not because the story is finished forever, but because this part of the story has been properly filed. The lamp continues to glow, the mug continues to send up its thin ribbon of steam. Outside the window, the sky remains dark, and the distance remains patient. And somewhere in that distance, whether soon or later, there is a spacecraft named Orion, a rocket named SLS, and a mission plan called Artemis II, waiting to make its quiet loop around the moon. For now, though, you don't need to follow it any farther. You can let the trajectory hold itself. You can let the data be collected without you. You can let the moon drift by in the mind's window, steady and pale, and you can rest. Good night.